Okay, so we've got our notation, and if you don't remember that, go back and look at the last video. Well, what we're going to do now is we're going to start building up our multiple linear regression. Again, some of this is recap, but we'll build up and get bigger and further. So, what we're trying to do with our multiple regression. So, what we'd like to do is we want to model the relationship between a predictor variable, x, and a response variable, y. So in the very simple regression model, we have a single predictor, x, which is fixed and known, and then we see some values in a response variable, y, and we'd like to build up the relationship of that, usually with a nice straight line. But in multiple linear regression, what we're going to do is we're going to have multiple predictors, which we're going to denote x1, x2, up to xr. So we've got r predictors, and a single response y, and the y is a real number. Why I say it's a real number is because later in this course we'll break that sort of assumption. And what we'd like to do is we'd like to, in multiple regression, say let's model the simultaneous influence of the predictors on y. So it's our first predictive model that you're going to see. So what is our data going to be? Well, it's going to be vectors. And for each vector, we have a response variable, y, and then we have some values of the predictors. And look at the notation. The first number in the subscript tells us which observation is. So all the ones that from the first subject are 1s, the second subject are 2, and altogether in this case we've got n subjects, so the last vector is all the subscripts start with n. On the x, the second number tells us which variable. So x11 says that is the value we observed for the first predictor on the first subject. All the way to x1r is the value we observe for the rth predictor for the first subject. Okay, so that's our data. What about our model? Well, we're going to assume that our yi is a linear combination of the predictors. We're going to have an intercept, which we'll denote as beta 0. And then we've got some beta 1, so that coefficient beta 1 times our xi1. So the I tells us we're considering the ith subject. The xi1 tells us this is the first predictor variable for the ith subject, plus beta 2, xi2, plus ... all the way up to plus beta r, xir. So that's just, to some extent, the multi-dimensional version of a straight line. But it's basically a linear combination. The reason it's called linear regression is that we're basically taking a linear combination of these coefficients, beta 0, beta 1, beta 2, up to beta r, times our predictors. Plus, we're going to have a noise term, which we're going to denote as ei. You can call that epsilon I, I've just called it ei in this case. And they are basically realizations of some independent random variables. They're very specific random variables at this point. We're going to assume that the expected value of each of these random variables is 0, and the variance of each of these random variables is sigma squared. So this is the deterministic bit. This bit here describes the relationship between our predictors and y, and this adds noise. And because this has noise, this is also going to be a random variable. And we've assumed at this point some information about this noise. We're expecting the mean to be 0 and the variance is sigma squared. They all have the same variance at this point. And again, these are things we can start breaking. Alternative forms, well, what we could do is we could actually add some extra stuff on this ei, which is the most common one you've seen. So now instead of them just having a mean of 0 and a variance sigma squared, we're actually going to name their distribution. They're going to be normally distributed with the mean of 0 and a variance of sigma squared. They have homoskedasticity or constant variance. They all have the same sigma. What does IID mean? To remind you, it means independent and identically distributed. So each one of these things are independent of one another. That is, there's no relationship between them. They all have the same distribution, and that distribution is then normally distributed with a mean of 0 and a variance of sigma squared. So this is our model in terms of, our random variable yi and our random variable e. But we're going to put this in a matrix formulation. Much easier. So we talked in the last video about random vectors. So here I'm going to put all my response variables, my y1 up to yn. So this is an n by 1 column vector of my response variables. Then I've got this X. This X is really special. We call it the design matrix. It tells us all about our predictors. The first column is 1s for the intercept. And then you can see this row here is all the observed predicted values for the first subject. Then the second subject all the way up to the nth subject. This column here is going to be all the observations for the first predictor. The second predictor all the way up to the rth predictor. We're going to put all our coefficients in a single column vector here. So this is of size r times 1, and it starts with beta 0, then beta 1, etc. And then we're going to put all our random noise terms here, our epsilons, in a random vector of size n by 1, where it goes from 1 to n. So now the model we discussed before is that y equals x beta. So by doing this x beta, when we do this multiplication, we are going to get lots and lots of simultaneous equations. Or in terms of our random variables, y equals x beta plus epsilon. Again, we need to define our epsilon. So we're going to say the expected value of our epsilon is 0. The variance, it's an identity matrix of size n by n. So basically it's zeros, everything in that matrix except for 1s along the diagonal. And in fact, it doesn't have 1s on the diagonal because we're multiplying by this scalar. So along the diagonal, we just have sigma squared, sigma squared, sigma squared, sigma squared. And because this is your variance covariance matrix, this random variable, because the off diagonals are all 0, all the covariances are 0, so therefore, well, they're not independent. I'm jumping to conclusions here. They are uncorrelated. But because we're going to add in this extra assumption of normality, one of the nice things about normality is if two variables are uncorrelated, that is the covariance is 0, it means they're independent. It's just a really nice thing about the normal distribution. So as I said, we can add in, I've already jumped ahead, we're going to add in that extra additional assumption of normality, which is our random vector, epsilon, is normally distributed of n-dimensional, a 0 mean. So basically think of that as a column of size n, all of zeros, and we've got this sigma squared I, our variance covariance. Now, we just sort of said there's our design matrix X. But if we're going to use this X, we have to add an extra constraint to it. So to explain that constraint, let's think about linear independence. So let's consider a set of vectors, v1 up to vp. So we've got p vectors. And we're going to say they're linearly independent if, let's say I can find a linear combination of those vectors. So I'm going to take the v1 and I multiply it by some constant, plus another constant alpha 2 times v2 plus dot dot dot. So I've just done a linear combination between our alpha 1, alpha 2 up to alpha p and our v1 up to vp. And I find that when I do that calculation, I get the 0 vector. I get a vector that is all zeros. If they are linearly independent, that can only occur if the time that I get that answer is the time where all the alphas are equal to 0. So what we're saying is, to some extent, I can't find some non-zero constants I can multiply these vectors to and get the answer 0. If all these vectors are not linearly independent, we call them linearly dependent. Okay? What we mean by that is that basically we're saying that when they're linearly dependent, it means that one of the vectors I could write as the linear combination of the remaining vectors. Basically what we're saying by linearly dependent is one of them I can make up from the rest. If they're linearly independent, I can't. So, let's go back to that multiple regression model. Our y equals x beta plus e. And the main thing for this to be okay for us to work with, to be able to deal with, I need the columns of x to be linearly independent. That is, I cannot write any of those columns as a linear combination of the others. And I'm including the intercept in that. Why? I'm not going to go into details. It's in the handout. As I've said before, with these slides, you have the slides and you have the handout, which repeats the slides, but it has extra information. I have the proof in there for you to look at. But basically, the key idea is that if my columns are not linear independent, so let's assume that one of the columns of my design matrix I can write as a linear combination of the other, my beta is not unique. You could go and find a solution to this problem and have a beta. I could find a solution to the beta, and they could be different, and they're still the right solution. There isn't a unique solution, and what we want is a unique solution. We don't want some sort of multiple regression where, you could come up with a set of answers that describes the relationship. I can come up with a set of answers that describe the relationship, and they're equivalent. So the other thing is at some point we're obviously going to be starting inverting things, and if they're linearly dependent, the columns, you can't basically get an inverse, and if you can't get an inverse, you can't solve it. But the main thing is we don't want two possible answers, and by having this extra constraint, we've locked it down to one possible answer. So I keep talking about this answer, let's sort of go into that in more detail. What do I mean? Well, I want to estimate these coefficients in my model. I'd like to know the relationship, and these coefficients describe the relationship. And there's different ways I could do this, but the way we're going to do is what we call the least squares estimate. So we know it's an estimate. That is, we're trying to guess. We know out in the sort of the truth there's these betas, and we want to guess what these betas are using our data. So we're going to estimate them, and we're going to define this as an estimate by saying it's beta with a hat. Remember, the hat basically is my notation to remind me that I'm guessing the value, or what we call an estimate. And how are we going to do that? What we're going to do is we're going to try lots and lots of different values of betas and find the one that minimizes the sum of squares. What do I mean? Basically, I try a set of betas. I go the observed values minus my x times that beta. I square them all, I add them all up, or in vector notation, I've got the norm squared. That function, I'm going to try my betas and I'm going to solve it such that I find the one that minimizes that. Once I've minimized that, that gives me my betas. Once I've got my betas, I can then go and actually, if you think about my model, I've got all the betas I want to estimate. I've also got that sigma squared, that variance term. And that I can estimate, the variance I can estimate and denote by SE squared, by basically take observation, minus off my predicted value from the model, square it all, and then divide by the degrees of freedom, which is n minus p, where n is how many observations and p is basically how many guesses I've made. So altogether I had the r, the beta 1 up to beta r, plus an intercept, so p is going to be r plus 1. And that's the rough rule of thumb. Your degrees of freedom is every time I put a guess in here, I lose a degree of freedom. So here I've made r plus 1 guesses. You should have seen this in stats modeling inference. If you haven't, go and look at it. It's a standard proof. But basically, I don't need to try everything. I don't need to code this up. We can actually either use linear algebra or we can use calculus to show that the solution is that beta hat is x transpose x to the minus 1 x transpose y. And you can see this bit here, the x transpose x to the minus 1, will not be defined if your columns are not of your design matrix X are not linearly independent. Okay, so that's how R's doing it under the hood. It doesn't actually do it that way. Basically, you should know if you've ever done numerical methods, you never try and invert a matrix. It uses other methods to do this, but this is the mathematical construct of how we're doing it. What if I want to get the fitted values? Well, I would just basically substitute in my beta hat. So it's going to be x times beta hat, which we denote by eta hat. Remember, eta is the expected value of our y. So if I substitute in beta hat, that's going to be x transpose x to the minus 1, x transpose y. This thing here, this x transpose x to the minus 1, x transpose y, will come back again, again, again. So we denote it as either P, because it's a projection matrix, or occasionally you will see it H when we talk about leverage. So H when we talk about leverage, P when we talk about projection matrices. And if we get time in this course, we're going to look at how you can define this whole thing in terms of subspaces and projection matrices. So just as a signpost here, hopefully we'll get back to this in this course and talk about why it's called P. What about the properties? So we've got these estimates. And we'd like to know some properties. We'd like to know what the expected value, are they unbiased? How much do they vary? Because then we can start doing hypothesis testing and confidence intervals. And that will be next time. Thank you very much.